Have you ever noticed the patterns on a football or the facets of a crystal? These are polyhedra, solid shapes with flat faces, straight edges, and sharp corners. They're everywhere, in architecture, crystals, even molecules. Now think about the right-angled triangle, a shape we all know from school, flat and simple. It seems worlds apart from the complex beauty of polyhedra. Geometry often treats these as separate triangles on a flat plane, polyhedra in space. But what if the leap from 2 to 3 dimensions isn't a leap at all? Imagine if every three-dimensional polyhedron could be traced back to a single right-angled triangle. This is the heart of the Grant projection theorem. It suggests we don't need to start with 3 dimensions to get three-dimensional shapes. Instead, we can begin with a humble right triangle and watch as the world of polyhedra unfolds from it. The connection between the simple triangle and the universe of polyhedra is closer than anyone imagined. This idea changes everything we thought we knew about where these shapes come from. The Grant projection theorem claims something remarkable. Every uniform polyhedron, from cubes to star-shaped solids, can be generated from a single right-angled triangle. The process? Reflection. Start with a right triangle, reflect it across one side, then another, and keep going. Each reflection adds a new triangle, building up a pattern like a dance, with each side dictating the next move. As you repeat these reflections, the triangles begin to fold and connect, enclosing space and forming a three-dimensional structure. The angles of your starting triangle determine the final shape. Choose a triangle with 90, 45, and 45 degrees, and you'll get a cube. Pick different angles, and you might get a dodecahedron or icosahedron. You don't need to know the outcome in advance, just follow the reflection rule and the shape emerges naturally. Traditionally, we define polyhedra by their faces and edges. The Grant projection flips this. Start with a triangle, reflect, and let the structure emerge. Complexity is built from simplicity. This method unifies the creation of all polyhedra. No need for separate rules for each shape. The only ingredients, one triangle and one rule: reflect. The resulting polyhedron, whether simple or intricate, is an emergent property of this process. It's a bottom-up approach to geometry, where the universe of shapes grows from a single seed. The Grant projection theorem reveals that the world of polyhedra is not a collection of isolated objects, but a family born from one simple idea. All you need is a triangle and a mirror. For centuries, Euler's formula, vertices minus edges plus faces equals 2, was treated as a fundamental law of polyhedra. It seemed like a magical property of three-dimensional space, but the Grant projection theorem shows that Euler's formula isn't a rule you must follow. It's a result of the reflection process. As you reflect triangles and build shapes, the numbers of vertices, edges, and faces naturally fall into balance. The formula emerges automatically from the construction. It's like baking a cake. Follow the recipe, and the result is guaranteed. Euler's formula is not a goal, but a consequence. This perspective demystifies the formula. It's not a law imposed from above, but the signature of a generative process. The triangle and its reflections are the cause. Euler's formula is the effect. This insight transforms a mathematical curiosity into a predictable feature of a constructive system. The beauty of polyhedra is not in their rules, but in the process that creates them. We often think of polyhedra as either familiar, convex shapes like cubes or wild, spiky forms like the great stellated dodecahedron. Traditionally, these were seen as separate families, each with their own rules. But the Grant projection theorem unites them. Both convex and stellated polyhedra arise from the same process, reflecting a single right triangle. The difference comes from how you connect the reflected triangles. Connect them one way, and you get a smooth, convex shape. Connect them another and you get a spiky, intersecting form. It's like building with the same set of Lego bricks, just assembling them differently. Stellated polyhedra aren't outliers, they're natural siblings of the convex solids, sharing the same genetic code. The great stellated dodecahedron isn't a more complex version, it's an alternate reality, born from the same process. This unified framework brings order to what once seemed like separate kingdoms. The world of polyhedra is one connected landscape. As you reflect triangles to build a polyhedron, you create a net, a flat pattern meant to fold into a shape. For simple shapes, the net lies flat, but for more complex polyhedra, the triangles refuse to stay in one plane. This non-planarity isn't a mistake. It's a signal. It means you're about to create something more intricate. The tension forces the structure to bend and twist, giving rise to new forms. It's like trying to wrap a basketball with flat paper. You can't do it without wrinkling. In the Grant projection method, this wrinkling is essential. Non-planarity is a mathematical instruction, telling the system to build something richer. What seems like a problem is actually a generative tool. The most interesting shapes emerge where things don't fit together perfectly. Sometimes, beauty in mathematics comes from creative tension, not perfect alignment. Polyhedra were once seen as a finite collection: Platonic solids, Archimedean solids, and a few others. But the Grant projection theorem reveals infinite families, like prisms and antiprisms, all generated by the same process. Vary one angle in the starting triangle, and you smoothly transition from a triangular prism to a square prism to a pentagonal prism, and beyond. Instead of endless separate cases, you have a single, continuous spectrum. The polyhedral world is not a static museum, but a living ecosystem of interconnected families. The same principles that build a cube also build a 17-sided antiprism. The theorem provides a unified origin for both the famous and the infinite ranks of lesser-known shapes. The universe of polyhedra is vast, and now we have a map that connects every address. Complexity and infinity emerge from a single, simple rule. In polyhedra, duality means every shape has a partner, like the cube and the octahedron. Traditionally, duality is a transformation you perform after building a shape, but the Grant projection theorem shows duality is present from the start, in the choice of the generating triangle. Convex and stellated forms are duals in a profound sense, both emerging from the same process. One interpretation gives you the convex solid, the other, its stellated counterpart. The process that creates a dodecahedron also creates the great stellated dodecahedron. They're two sides of the same coin, sharing a common origin. Duality is not just a trick, it's a fundamental symmetry at the heart of creation. The polyhedral universe is woven together by hidden harmonies. What about higher dimensions? Mathematicians dream of four-dimensional shapes like the 120 cell made of 120 dodecahedra. Traditionally, you'd need new rules for higher dimensions. The Grant projection theorem offers a different path recursion. Take the process that builds a polyhedron and treat it as a new building block. Apply the same reflection principles to this block, and you construct a four-dimensional polytope. You're not adding a new dimension, you're adding a new layer of complexity. The 120 cell emerges by recursively applying the three-dimensional method. Higher dimensional shapes are not fundamentally different, they're extensions of the same core idea. The same seed that grows a cube can, with recursion, grow a 120 cell. Unity across dimensions comes from process, not space. The journey to higher dimensions starts with a single triangle. In classical geometry, we assume a dimension, 2, 3, or more, and then build shapes within it. The Grant projection theorem turns this upside down. Here, dimension is not a starting point, but an outcome. Begin with a right triangle and reflection rules. No dimension specified. As the process unfolds, the structure organizes itself, and its dimension emerges naturally. If the pattern tiles a plane, it's two-dimensional. If it folds into a volume, it's three-dimensional. Recursively, it can become four-dimensional. Dimension is not a pre-existing box. It's a property that arises from the shape's internal logic. This is revolutionary. Space itself can be built from the bottom up. We don't need to assume a three-dimensional world to explain three-dimensional shapes. Dimensionality emerges from simple, repeated rules. The complexity of our world may be the result of a humble triangle in a mirror. The secret was hiding in the triangle all along.